Did I copy 49? Of course I copied 49. Okay, never mind. Okay, we want 48. 48 it is. She's bossy. So f of x, I'm kidding, 5 plus 54x minus 2x cubed. And by the way, I'm so happy to be with you. It makes me forget of what's out there. Anything to distract me from. Okay, so obviously I want to arrange everything in descending order. So did I copy it correctly? I think I did. Okay, we have to find a prime. So negative 6x squared plus 54. I will get my table going. Can everyone see? Am I on in the viewing? Can you see everyone?
Yes.
Yes? Okay. So then I will solve the equation f prime of x being 0. There is no discussion for f prime of x being undefined because this is a polynomial function, it's quadratic. So from here I have that negative 6x squared plus 54 equals 0, or x squared is 9. How many solutions I expect here? Yes? The best thing to do is to take square roots. So x equals plus or minus 3. However, the domain that I'm given is 0 to 4. So I can't have anything else but 3. Negative 3 is out here. Who cares about it? Good. So I study the sign of the derivative. Again, it is a quadratic function with a negative leading coefficient, a negative, positive, and negative. So to the left of the first solution is negative. Between these two solutions, it's positive. And outside is negative. Or you just plug in numbers. At that point, I have to find these values. I know that when x is 0, I get 5. But for the other two, I'd rather put in the calculator. I'm lazy. So I have negative 2x cubed and plus 54x and plus 5. I put in the calculator because I want to determine, nope, I meant this. So I want to plug in 3 and 4. 3, enter, 4, enter. I got for 3, 113. And I got for 493. So now at this point, and I'm going to say that many times from moving forward, at this point, I check my work. If these two rows do not work well together, I'll say, oops, I have an error. From 5 to 113, what should the function do?
Increase.
Is that supported by the sign of the first derivative?
Yep.
Yes. From 113 to 93, what should the function do?
Decrease.
Is that supported by the sign of the first derivative?
Yes.
So then I know that these work well together. Now, I picture this in my head. The 5 here, the 113 here, and the 93 here. So this is 93, this is 113, 93, and this is 5. So what does 0, 5 represent?
Absolute minimum.
Excellent. What does 3, 113 represent?
Local and absolute max.
And what does 4 comma negative 4 comma 93 represent?
Nothing.
Very good. Do we feel better about this?
Ease.
Yes? Do we need other examples, or you think we can continue with 4.2? We have to look at 2 theorems.
Before we move on, can you explain when is it, like, what's the difference between, like, local absolute, when can it be both?
The local
I
what?
guess I'm really just asking when can it be both.
This one is both. Local and absolute max. But this one cannot be both, because the function does not exist to the left-hand side of 0.
Okay, I get it. Thank you.
Yes. So for a local, I have to be able to show the open interval. If it's like this or like this, if this point exists and this one does not, I can still show an open interval because the function exists at both sides of this point, and all function values are smaller than this one. So this will be local, because it continues and it has higher values than the local max here. So it's not an absolute. But when it comes to something like this, the function has here, right here, an absolute min and also local. But this one, it's not a local max because the function does not exist on this side. I don't know if it's going this way, that way, so it doesn't exist, so there is no discussion. This is nothing. What about this? Is this local? No, because I cannot show the open interval. So this will be an absolute max. This will be an absolute min and local min. This will be nothing, and this will be just absolute max. Is this better? Okay, I'm assuming you will stop me if you have questions. So we're ready to, if you don't have anything else, we're ready to move on to 4.1. There are 2 theorems here that we are going to look at. One is called Rolle's theorem. Let's take a look at the following function. Here's A, here's B, and here's a function that does this. Or if you want a slightly more complicated, then we can do this. It doesn't matter regardless. There are 3 hypotheses. Three hypotheses of this theorem. Number 1, f continuous on a comma b. Would you agree? No matter whether it's this situation or that situation or as many as you want, turns in there, it's still continuous. Number 2, f differentiable on at least a comma b. You may have a vertical tangent here, but I don't care. It's differentiable between a and b, doesn't have to be differentiable at a and b. And the third hypothesis is that f of a and f of b, looking at the graph, must be
Equal.
excellent. Then, by Rolle's theorem, of course there exists a c in the open interval a comma b such that there exists at least one c. Such that I'm waiting for you.
F prime of c equals 0.
Excellent. Guaranteed by Rolle's theorem. In other words, if a function is continuous and differentiable and starts here and comes back to the same level, it must have at least one term. If it has a term, the function has a derivative that is 0 there. Can it have more? Yes. The derivative must be 0. So here f prime of c is 0. Here it has c1 and c2. So f prime of c1 is 0. And f prime of c2 is 0. Great job. Let's look at an application. On page 288. One, two, three, or 4. You choose. Or I will. One, two, three. Okay. I chose 2. So f of x equals x cubed minus x squared minus 6x plus 2. The interval is given to us. Verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval. Then find all numbers c that satisfy the conclusion of Rolle's theorem. Okay, number 1. What do I have to write? To make sure, not just write, but to make sure that the function is continuous on AB. Is this function continuous on 0, 3?
Yes.
Exactly. That's all I wanted you to say. F is continuous on 0, 3 as a Poly function 2. Is this function differentiable on 0, 3? For the same reason. Number 3. Is the third condition fulfilled? I have no clue. I have not checked. So I have to find f of 0 and I have to find f of 3. If they happen to be the same, then I can find c. If any of these conditions fails, Rolle's theorem is not applicable. I showed it's continuous as a polynomial function. I showed that it's differentiable always as a polynomial function. And I'm determining f of 0 and f of 3. F of 0 is nice, no problem. For f of 3, what do I have? I have 27 minus 9, minus 18 and plus 2. So this is, it was 3, right? Yes. So 27 minus 9 minus 18 and plus 2. So this is 29 minus, I'm getting 27. Yes, okay, good. So all three conditions, not both, all three conditions are fulfilled. Therefore, from 1 and 2 and 3, by Rolle's theorem, there exists C, at least one, guaranteed, in the open interval 0, 3, such that, as you said, f prime of C is 0. But I have to find f prime of x. Well, f prime of x is 3 x squared minus 2x and minus 6. Is this okay so far? Good. So now I have 3c squared minus 2c minus 6 equals 0 because I have to create this equation. And yes, you can solve it in x if you want to and then just say that is c. That's fine too. That's fine. Okay, so I will use the quadratic formula. And I have negative b plus or minus b squared minus 4 times a times c, which is negative 6, and I prefer doing this, over 2 times a, which is 6. And I'll grab my calculator. Don't forget to put parentheses around the numerator, and I recommend parentheses inside the square root as well. So parenthesis 2 plus the square root in parentheses, that's me, so 4 plus 12 times 6, close the parenthesis outside and divide by 6, 2 times 3, yes. I repeat, overriding plus by minus, and I got two solutions. C equals 1.79 approximately, and C equals approximately negative 1.12. Remember, we are talking about at least one in the interval 0, 3. This is in the interval 0, 3. This isn't, but it's at least one is guaranteed by Rolle's theorem. So why is this helpful? Now I know that between 0 and 3, the function has a point of extrema. Point of extrema means max or min. Do I know whether this is a max or min? No, I don't. Because it could give a minimum. I'm going back to the previous. So it could be that C1 here gives a maximum, but here C2 gives a minimum. But I know that definitely between 0 and 3, the function has a term. It could be max or min. It's guaranteed by Rolle's theorem. It starts at the same point, comes back to the same point between 0 and 3. I don't know if it does this or this. But I know it has a term between 0 and 3, either a max or a min. Guaranteed by Rolle's theorem. Any questions? Is this okay?
I have a question.
Yes, please.
For number 2 in the theorem, f is different on 0, 3. Can you just go over that one last time?
Which part? Sorry.
For the second part of the theorem.
This one?
Yes.
Polynomial functions are differentiable everywhere. Polynomial functions do not have, they are continuous everywhere, but don't have corners, cusps, or vertical tangents. So by definition, polynomial functions are always continuous and always differentiable. And this is a polynomial function.
I understand now, thank you.
Sure. Thank you. Other questions? So, we didn't graph them yet. In this chapter, we're going to graph polynomial functions, not how we did it in pre-calculus. But as you know, for example, degree 3 polynomial function either looks like this, if it has a positive leading coefficient, or looks like this, if it has a negative leading coefficient. Oh, these functions, any degree, I just picked degree 3. These functions don't have a cusp ever, don't have a vertical tangent, ever, don't have discontinuities, don't have corners. So these are continuous and differentiable everywhere on their domain. And this is valid for any polynomial function. Good. Would you like to choose another example, or is the idea clear? And what we learned from Rolle's theorem about a function. We learned that it must have a term. If it fulfills all 3 conditions of Rolle's theorem between, in this case, and for this function between 0 and 3, we know it has to have a term. Rolle's theorem doesn't tell us if it's a max or a min, though. We have to go back to what we did before. What we did before, I'm going back to the notes. What we did before was this study for the derivative, the sign of the derivative, and then we know what happens there. And we didn't do that. Oh, we can, but Rolle's theorem doesn't tell us what type of point that is. It just guarantees a term. Would you like to pick another, or we move on to the other theorem, the second one?
Can we do one more?
Yes. Would you like to choose, or you want me to choose?
You can pick.
Okay, so let's do 3. So 3 on the same page, 288. And the function is the square root of x minus 1/3 x on the interval 0, 9. Do you want to work on this for 1 minute? It's up to you. If not, I will. Any decision? Any decision? Okay, I guess I would start. So first of all, on the interval 0, 9, this is always defined. This is always defined. So I will write f of x is continuous on 0, 9 as a difference or sum two continuous functions there, right? Continuous functions. Because this is always continuous between 0 and 9, and this is a linear function. Number 2, f of x is differentiable. Careful, because we know this is not differentiable at 0. But on the Rolle's theorem does not require the function to be differentiable at the endpoint, and this one isn't. For the same reason as a sum or difference of two differentiable functions on the interval, for sure. This is always differentiable. This is always differentiable between 0 and 9. Now, in number 3, I have to find f of 0, and I have to find f of 9. 0 is easy, it's 0, but f of 9 is the square root of 9 minus 1/3 times 9. So this is 3, and this is 3, indeed is 0. Since all three conditions are fulfilled, I will say, then, by Rolle's theorem, there exists at least one C in the open interval 0, 9, such that f prime of C is 0. Of course, I have to look at and determine f prime of x first. And I get 1 over 2 the square root of x and minus 1/3. Then I would write 1 over 2 the square root of c minus 1/3 equals 0. And then how do I solve this equation? What I would like to do is write 1 over 2 the square root of c equals 1/3, and then cross multiply. There is no need. If the numerators, if the two fractions are equal and they have the same numerators, the denominator has to have to be the same. Or just cross multiply is the same thing. So then the square root of c is 3/2. We square both sides to get 9 over 4. This is guaranteed to be in the interval 0, 9. It says 2.125. So obviously it's between 0 and 9. Guaranteed. So what does this mean? It means that the function that we started with, what was the square root of x minus 1/3 x, must have a term on the interval 0, 9, must have a max or a min on the interval 0, 9, guaranteed by Rolle's theorem, at c, or x if you want, 9/4. Any questions, please? Does it make sense? Does it make sense?
Yes, it does.
Okay. You think we are ready for the second theorem? We have about 10 minutes left. We can present a theorem and then stop. It's up to you.
That's fine with me.
Yes? Okay. So here's the second theorem. my page 17. Mean value theorem. The value in the middle theorem. I am opening up, because I told you I have 3 computers open. I wish you could see me. And I'm trying to start uploading one of your videos. Okay. Okay. The mean value theorem, so let's take a look. Here's the scenario. Here's a function. This is also abbreviated MVT. Like the IVT, the intermediate value theorem, this is MVT. Of course, our friend, the interval a comma b. This is point A, and this is point B. And I hope you agree, this theorem only has 2 hypotheses. The first hypothesis is obviously f continuous on a comma b. And the second hypothesis, of course, f differentiable on a comma b. Only 2. As you see, the third one is not a requirement here. And obviously they're not equal. F of a does not equal f of b. Then, by MVT, there exists a C, at least a C, in the open interval a comma b, such that, okay, ready? I'm looking for, I thought I had it here. I put it away. Okay, here it is. Ready? Would you agree? I'm just going to draw this in pencil. This is the line segment through AB. Can anyone give us the slope of the line segment AB?
F of b minus f of a over b minus a.
Excellent. Thank you. Awesome. Now forget about this for a moment, and here's what I'm going to do next. I'm going to draw a parallel to this line that is tangent to the graph. Any questions on this? Thank you, Jed. That was great. Any questions on this? Anyone? Okay. So, since this line, by construction, is parallel to this line, can anyone tell us anything about their slope? Their slopes?
They're equal.
Exactly. You already gave me this. So now I would like you to give me the slope of this line.
F prime of c.
Thank you very much. Very good. Of course, the slope of the tangent line at this point must be f prime of c. Oops. Great job. So, what does this say? It doesn't say that there is a turn there. Right? Because that's not the situation that Rolle's theorem represents. Rolle's theorem says, okay, it must be a turn if the function starts at that point level and comes back to that level. This message here is slightly more intrigued, if you want. So here we say that at any point on the graph, depending on the starting point and the end point, I can always find a point where the tangent line is identical with the line segment, the slope of the line segment going through the endpoints. Let's apply this. We have 5 minutes, so let's at least start a problem. And we'll have more on Wednesday. I don't know why I shut this book, it's just in the way, it's so heavy. Okay, let's look at problem 10, and on page 289. Verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Then find all numbers C that satisfy the conclusion of the mean value theorem. Okay, so we are given f of x is x to the third minus 3x plus 2, and we are given the interval negative 2, 2. Okay, so it's a polynomial function. 1 and 2 are definitely satisfied. So f continuous as a polynomial function on negative 2, 2. Oops. And f differentiable for the same reason on negative 2, 2. Then by MVT, there exists C, at least one, in the open interval negative 2, 2, such that f prime of C equals f of 2 minus f of negative 2 over 2 minus 2, minus negative 2. And this is guaranteed, and now I can shut the book and put it away. So that's guaranteed by MVT. So I have to find f of 2. Let's see, f of 2. 8 minus 6 plus 2, that is 4. I have to find f of negative 2. Negative 8 plus 6 plus 2, 0. I have to find f prime of x, which is 3x squared minus 3. I put f prime of c, which is 3, c squared minus 3 equals f of 2, 4, minus 0, over 2 minus negative 2, which is 4. So this is 3c squared minus 3 equals 1. Or 3c squared equals 4, or c squared equals 4/3. I take the square root, and I get plus or minus 2 over the square root of 3. And I will approximate. They have to be between negative 2 and 2. 2 divided by the square root of 3, 1.15, approximately plus or minus 1.15. And they are between negative 2 and 2.